Okay, thank you for sticking around so late. I'm going to talk. Can you read my writing? So I'm going to talk about an old problem in Kushilevitz-Nissan. I think it's in the first 5 pages. A couple of problems in the first 5 pages. And this is joint work with Mika Goose and Tom Watson. So we'll start with a two-party function, communication function, capital F, and it has its associated Boolean. It's a Boolean function. It has its associated communication matrix, and chi1 f is the minimum number of disjoint monochromatic rectangles that covers all the ones of the function. Okay. And chi0 is the same thing, but a covering of the zeros. Okay. And chi, which is the partition number of the function f, is the sum of these two. Okay. So it's just, you want to partition this 0, 1 matrix into the smallest number of monochromatic pieces. Okay, and that's called the partition number. And if you have a deterministic protocol for this function, it induces a partition, and the question is whether these two are the same. So in particular, the question is, so it's clear that the deterministic communication complexity of f is, which way do I want this, is bigger than or equal to the log of the partition number. And we also know that it's bounded on this side by the log squared of the partition number. And then the question is whether, which direction is the right one. Okay? And it was known that that the deterministic communication complexity is at least as large as 2 times the log of the partition number, and that's a result by, I think, Kushilevitz, Lineal, and Ostrovsky. I think he doesn't know, so it's okay. And what I want to show you today is that that this is closer to the right answer. So the deterministic communication complexity of f is bigger than or equal to is equal. And
there exists f, right?
Yeah, there exists f, certainly. Yeah, I could just have an all one matrix, and then it would be really easy. And so that's the first thing. And then I'll also show you that we can do better if we. Oh, what did I do here? Sorry, nobody said anything. You're nice. So I meant to say that. So the deterministic communication complexity, suppressing a log factors, log factors, I guess it's at least as big as the log of the partition number to the 1.5. And if we look at chi1 instead, then we get the square. And this is tight because actually this result here, it really holds for chi1, not just for chi. Okay. And this is easy to see, but I won't do it today. Okay. Sorry. Thank you. Okay. So just a few little things I wanted to mention. So applications or consequences. So this is just we're getting, first time we've gotten a better than linear lower bound, and I don't know what the right answer is. I don't know if it's 1.5 or 2. I've thought about it, and so that's still open. But I wanted to tell you a little bit about this. So this question of
Does that statement also applies to chi0?
This statement, yeah, I guess you can just look at the negation.
So I don't know, one of chi0 and chi1 is at least half of chi.
Oh, this is because I'm taking logs.
Yeah, but that's even... No, I'm saying, so if you have the lower, the thing below... Oh, I see. And then, for your example...
You'll see, yeah, you'll see.
Chi1 is much
Yeah, you'll see. Yeah. Okay, so first of all, this question.
I don't understand. So why can't you apply it to chi0? So one of chi0 and chi1 is at least as much as...
It's not the same. It's
the same.
It's not the same.
It exists an F. Yes.
So it might not be the same f that has.
Oh, the second theorem is...
Sorry. Yeah. In general, it has to be exists f, otherwise it doesn't make sense.
Oh.
Is that okay? Okay, so one consequence, and this is really not a consequence, it's like another way to state the same thing. Yannakakis studied this clique independent set problem, and this is a communication problem where you have an underlying graph that the players both know, and one player is given an independent set of the graph, and the other player is given a clique, and they want to know whether they have a vertex in common. And this problem is, it's basically complete for these kinds of protocols. So non-deterministic protocols where there's a unique witness. Because obviously if you have a clique and a co-clique that intersect, they can only intersect in one vertex. Okay? So this problem is complete, and so you get this tight result for Yannakakis' problem. Okay? And before this, it was known quite recently, actually, Mika proved a lower bound for this problem, therefore, and also this problem, and I think it's something like 1.1 chi1. So we weren't the first people to. So this was the first result that did better than that got something non-trivial for the problem. This is a little bit incomparable because he actually proved it for co-non-determinist. So his lower bound is not. It's not just a deterministic bound; it's a co-non-deterministic lower bound. So it's a bound for a stronger communication model, but the numbers are not as good. His proof is. So our proof is easy, really easy in one sense, and more difficult in another sense, and I'll tell you that in a minute. And secondly, we get a new lower bound for the log rank conjecture, and this is just because so the deterministic communication complexity is at least as big as. Make sure I get my directions right. So if you have, so the log, do you know what the log, so the log rank conjecture is the conjecture that the deterministic communication for any function f, that the deterministic communication complexity of the function f is more or less equal to the log of the rank over the reals of f raised to some polynomial. Okay? So it's a beautiful conjecture, and it's stating that basically, for any Boolean function f, if you want to understand its deterministic complexity, all you have to do is know what its rank is. Okay, that they're within a polynomial factor of one another. It's a long-standing open problem, and most people have been working on upper bounds. And the best upper bound is something like by Shahar Lovett. It's something like square root of the rank with some log factors. And what we get is a lower bound that. Okay, and this is easy. It just follows because, yeah, all of this is existent. Yeah, and this is just easy. This is just because if you have, if you have a deterministic protocol, you have however many the monochromatic 1 rectangles. That's the rank of the matrix is at most the number of monochromatic 1 rectangles, which is chi1. Okay, so our quadratic separation between deterministic complexity and log of chi1 of x gives this. Okay, and before, the best that was known, I think, was something like 1.26. Something like that. So questions?
Yeah, is there an upper bound for the theorem too?
Yeah. So I said that, but just briefly. The upper bound holds for chi of f, but also holds for chi1 of f. And it's really just it's a divide and conquer algorithm. You look at the degree of the clique. You find a vertex of degree. Yeah, it's a binary search. So I want to give you some idea of how this goes, because it's surprising, I think, that the proof is actually pretty easy. And I'm going to give you a 3-step program for proving. I'm going to prove hopefully both of them, but I'm going to I'll start with this one, and then we'll use that one to prove this one. Okay. So I'm going to give you a 3-step program, and this is a program to prove communication complexity lower bounds, and we really like it. And if you're having trouble with your other programs and you're having nightmares about shears inequality and the chain rule, you might want to try this program. It incorporates elements of information theory in it, and it can often be used when other approaches fail. So the first thing you have to do is you have to work with composed functions. And I'm sure a lot of you have seen this before, by the way. We're not claiming that this is our method. So the communication complexity functions that we're going to work with they're going to be a composition of two functions, f and g. And I just want to say that this general technique, it's been used in a lot of places, not just in communication complexity. So it's been used in communication complexity all over the place. One notable example is a lot of Scherstoff's work, but there's lots of others. It's really behind a lot of the work in extended formulations. It's behind like the monotone switching network lower bounds of Pitassi. The list goes on. It also comes up a lot in proof complexity lower bounds. And the basic idea is if you work with composed functions, that your life is much easier because you can study the complexity of the outer function f in much simpler models and then lift it to study the complexity of capital F in your stronger model. Okay, so we're going to look at composed functions, and f is going to be a Boolean function. Yeah, that's the outer function on n bits. And g is going to be the inner function, and it's some gadget. And in this talk, g is going to be the indexing function. So today, g is going to be the indexing function. So Alice is going to get an index or a coordinate, and Bob's going to get a string. And g of AB is going to be, so A is going to point to a location in the m-bit string B, and they're going to output, they're going to output B sub A. Okay? So just the usual indexing function. And M is going to be some polynomial in n, like say n to the 10th. Okay? And then capital F on some input. So take x, y, x in x to the n, and y in y to the n. So capital F of xy is just going to be f applied to g of x1, y1, g of x2, y2, and so on. Okay. And like I said, g is always going to be the indexing function, and little f, I'll tell you about that next. Okay, so that's the first step to work with composed functions, and then we're going to study the query complexity, which is a much simpler computational model of the outer function little f. Okay, so we're going to try to prove our separation in this much simpler query complexity model. Okay, and even if you don't know what this is for now, I'll tell you what it is in a minute. But it's basically going to amount to decision tree complexity, and more generally, it's going to be like a oracle version of whatever complexity class we're talking about. Okay. Okay, and then, like all k-step programs, you have to appeal to higher powers, and in our case, it's Ross-Mackenzie. So this is, let me get down here and write this. So we want to lift the result to the communication complexity world via a general transfer theorem. And this is going to be a theorem. Like I said, for us, it's going to be Ross-Mackenzie, but you can use other higher powers if you want. There's several theorems of this form that are quite nice, and depending on the model, you can use different ones. But we'll use the Ross-Mackenzie. Well, we're going to have to modify the Ross-Mackenzie one. But let me just tell you what. Let me just start with that. So basically, you have a general theorem that's going to allow you to take the lower bound that you got here in the query complexity world and basically lift it to get a lower bound in the same model for the communication complexity class for the composed function. Okay. So what's this theorem? So this is the Ross-Mackenzie theorem from a 1999 paper, and this is not how they stated the result. They actually stated and proved it for a more special case of this, where it was for CNF search problems. But if you're brave enough to go through the proof, they actually proved this more general theorem. And in our paper, we simplified the proof somewhat, streamlined it, and we think that it's much easier to understand now. It's given as an algorithm that takes you from a communication complexity protocol for the lifted composed function and produces a decision tree for the little f. Okay, so the theorem states that for any f, and for the g that I mentioned, the decision tree complexity, this is my notation for decision tree complexity of the composed function, is equal to the, this should be communication complexity of the composed function is going to be equal to the decision tree complexity of the outer function times some log n term. Okay, and this is basically inequality. Okay, so this is saying that.
I'm sorry. This is for g equals index.
This is for g equal to the index function. Yeah. So what is this saying? This is saying that all you have to do is prove a decision tree lower bound for f, and you automatically, for free, get the same lower bound with this extra log factor for this composed function. Okay. Now it's easy to see one direction. If you have a decision tree for f, then it's easy to see that you can get a communication complexity protocol for this. The players just follow the decision tree, and since Alice's input is small of length log m, which is order log n, anytime they want to decide, the value of one of these meta variables, Alice just sends her order log n bits to Bob, and he sends back the index value. Okay, so that's the easy direction, and the hard direction is basically the theorem that you can go the other way around. That you can take a communication complexity protocol for the composed function, and you can extract from it a decision tree, and the complexity of the decision tree is this divided by log n. So I won't be able to tell you much about this proof of this today, but it's really nice and really not bad. It's very natural, and it does use concepts, information theoretic concepts. But I'll show you how we can use this theorem. So use this theorem to at least prove, maybe they're both quite easy once you have this. Okay. Well, you need another idea. You need to prove the query separation. So let me just state the query versions of the theorem. So theorem 1 prime, this is the simpler query version of the theorem that we ultimately want. So this theorem states that the decision tree complexity there exists in f, so that the decision tree complexity of f is omega, so bear with me, I'll tell you what this is in a minute. So this is more or less, I'll explain these in a minute. So this side is clear. This is the decision tree complexity of f. And on this side is the query analog of log of chi1 of f. Okay, what is this? UP stands for unique p. So this is, in the non-relativized world, this is the class unique p. So you have a non-deterministic, it's the complexity of the non-deterministic, Turing machine where the witnesses are unique. And this 2UP is where the yes instances are unique and the no instances are unique. So the decision tree version of it is you want to rewrite f as the disjunction of a bunch of terms, and each term ti So if the UP decision tree complexity of f is at most k, then that means you can rewrite f as a disjunction of terms where each of these terms has size at most k, and for every one of the function, there exists a unique ti, so that ti of alpha is 1. Okay. Does that make sense? So this, I hope this should look like the natural query analog of the class UP. And 2UP is, like I said, the same thing, but you have it for the ones and for the zeros. Okay.
The size of TI?
The size of TI is basically the decision tree complexity in this model. So it's how many bits you have to look at to have a witness, and you want the witnesses to be unique. Okay, so now I want to try to show you how to prove. We'll do this one first. Okay. Anybody have any questions? So I wanted to say one thing. So this, one of these two, I forget which one. Let's see. Yeah, so this one here, there was a weaker version of this result that was actually already known by Safitsky, and I think he got like something like 1.26. So you can get something here without doing, just applying his query complexity separation to our modified version of Ross-Mackenzie. But I'm going to show you, an easier and better bound construction.
1.26 that you already saw.
Yeah. So with the modified Ross-Mackenzie in the Safitsky result, you get, yeah. Okay, so. So I want to do this one. This is the main one, and then this one is this one is easy once you have this, but you just take the and of a bunch of copies of this one to get this one. Okay, and the numbers degrade because we're taking the and. So we want to come up with Boolean function f, where the decision tree complexity is going to be about k, and the UP decision tree complexity is going to be about k squared. So. So. Oh, sorry. Yes, thank you. No, you're right. You're right. It should be this way. Okay, so let's start with a warm-up. This is, we're going to look at a function f on k-squared Boolean variables, and it's just a 0, 1 matrix, and we want to output 1, so we want to say yes on a 0, 1 filling in of this matrix if and only if there exists a unique column of all ones. Okay? So if you have a column, exactly one column that's entirely filled with ones, and no other column has all ones, then we want to say 1. So this separates P from NP. Okay, so what do the witnesses look like? Well, we have to find the column that has all the ones in it. That's k bits, and then for all the other columns, we have to identify a 0 somewhere. Okay. So that's roughly, that's like roughly 2k. I said k, but okay. Now this is not in UP because we'll get to the lower bound in a minute. But it's not in UP because these 0 witnesses are not necessarily unique. Okay, so we have to fix it up. And why is its decision tree complexity k squared? Well, the adversary. So when you're proving the lower bound, you get to pick the direction. Given any decision tree, the adversary gets to pick the direction to walk in. And so what's the adversary going to do? No matter what's queried, we're just going to always say 1 until we get to the last place in the column, and then we'll say 0. And we just keep doing that. So it's going to take, basically you're going to force the person to look at all k-squared things. Okay? And so how do we fix this up so that the queries are unique? I mean, not the queries, so that the yes instances are unique. So the way we'll fix it up, so we're going to have a matrix again. And instead of having just one Boolean value per entry of the matrix, we're going to have 2 values. We're going to have a 0 or 1 value in the upper part. So for example, here. And then the lower part is going to be a pointer to some other location in the matrix. Okay. So for example, here we might point to this one. You probably see where this is going. I'll point to here. Okay, and we're going to output 1. So if and only if, how do I say this? So basically, you want there to be, like before, you want there to be a unique column of all 1s, okay? And you're going to find, so one thing I didn't say, these can be pointers to other locations, or they can be bottom, okay? So so each entry of the matrix is labeled with a pair, where the first element in the pair is 0 or 1, and the second element in the pair is a log k number union with bottom. So it either points to another location in the matrix or it's bottom. Okay? And so what you want to do is you want to find, if it's a 1 instance, you want to find the all 1 column and then make sure it's all 1. And then then we want it to be unique. So the very first place in this column that's not a bottom, in this case it's here, you want to follow that pointer. Okay? And then you want to follow it and to get to a place that's the 0. Then that goes to another place that's a 0, and so on. Does that make sense? So it's a unique. So by doing this, following the pointer, we're going to get to unique 0 places in all the other columns. Okay. So a unique yes instance is exactly that. It's a column of all 1s together with, you take the pointer that's the first pointer in this column that's non-null. You follow it, that has to be a 0. Follow it, that has to be a 0, and so on. And you follow it k minus 1 times, and you should cover all of the columns, and you should see that they're all 0s. Does that make sense?
Why isn't this first pointer that's non-bottoming not always the last in the column?
It doesn't have to be. It can be here. You just, but the point is it's the number of matrix entries that you have to look at to verify that it's a 1 instance is about 2k again. Okay, because you check that all these are 1, and then you have to.
And you don't want to constrain it to be all the way at the bottom. Oh, I see.
No, I'm not constraining it to be all the way at the bottom. Yeah. Okay, so that's basically the function, and then to check that it. Am I over? Am I okay? Do I have another couple minutes? So to check that this has deterministic complexity k squared, it's really just sort of the obvious adversary strategy. As long as you ask about a location, you answer with 1 as long as you can, and you say bottom as long as you can. And when you get to the very last one, you say 0 and bottom. Okay, and you're basically filling in columns with all 1s and then 1, 0, and then we have to figure out how to do the pointers. So you basically want to do the pointers in reverse order. So the very first column where you filled it in with all 1s and a 0, okay, that's like the first one that happens. Then you look at the next one that gets filled in that way, and that one, that 0, the last one that was 0, gets pointed to the previous one, and so on. Does that make sense? So in that way, you're basically forcing k squared spots to be looked at. And this is not Boolean anymore, or if it is Boolean, these have size like order log n, but that's why I was suppressing the logs. Does that make sense? Okay, so that's how you get this separation, and then like I said, this one, you just take the and of, k independent copies of this, and you can check that in that case, the witnesses will be unique and will have length now k squared, because you have to have yes witnesses for each one. And you can also check that that if it's a no instance, that you have to check k cubed. You more or less have to check everything. Okay. And I think that's all I have to say.
Can you say something about the relationship between chi1 of f and this query thing? So the UPDT little f.
Oh, you mean why it is? Oh, so you mean you want to understand why chi1 corresponds to this class? Yeah. So if you think about it, chi1 is just you're just looking at non-deterministic protocols where the witnesses have to be unique. So, like, if you think about a communication protocol, is they make a guess and then they check to see if the guess is right. The chi1 is sort of measuring the unique one, and yeah, this is like the query version of that.
Replace terms with rectangles.
Okay.
I had a question. So your adversary strategy seemed to assume that when you query a pointer, then you're really querying the whole pointer. But what if I query only some bits of it?
Yeah, I'm just giving away for free. In the lower bound, I'm giving it away for free. So as soon as you query one bit, I'll give away all logs. So that's why we lose